All right, so let's take a look at number 74. A typical rate of deposit of dust fall from unpolluted air was reported as 10 tons per square mile per month. So we can set up a relationship here. 10 tons of dust per square mile per month. Express this dust fall in milligrams per square meter per hour. Okay, so here, this is an intensive, but we're going to start with this because all they want us to do is change this. So rather than tons of dust, they want milligrams of dust. Okay, so the first thing we're going to do is we're going to convert tons to milligrams. So let's go ahead and do that. Name?
Warda.
Warda?
Yes. I'm a history.
Okay. Warda, you were here on Monday, right?
Yes.
Just late. I thought I fixed that, but I guess I didn't. Okay, so we need to get rid of tons or tons of dust. In fact, we're just going to get rid of tons. And so where can we go from tons to pounds? And do you know the relationship? 2,000 pounds a ton. So the tons, now we have pounds of dust. And so where should we go from pounds to grams? This one you may or may not have memorized. The same thing with tons. Tons and pounds I'd give you. You don't have to memorize that. This one too I'd probably give you if you forget. But does anybody remember the conversion from pounds to grams?
1 pound is 453.6 grams.
453.6 grams. And so now we have grams of dust. And we want milligrams of dust, so it's 1,000 milligrams per gram. This one you have to have memorized. Okay, so we have milligrams of dust in the numerator, and then they want it per meter, square meter, not per square mile. So we have to go from miles squared to meters squared. And so if I want to go from miles, where can I go from miles? Now, what a lot of people do is they'll just Google it. They'll Google, how do I convert square miles to square meters? But you aren't going to be able to do that on tests. And I'm not going to give you the conversion, the direct conversion from square miles to meters. And so we're going to have to do this based on conversions that you should know. We can go from miles to what? Feet. This one you don't have to have memorized, but do you know what it is? 5,280 feet. Exactly. Miles. So that's infinite sig figs. So this is infinite sig figs. Here, 10 tons of dust. How many sig figs is that? 10 tons of dust per. So the way I'd read this is in exactly a square mile, in exactly 1 month, we have approximately 10 tons of dust deposit. Now, how many sig figs is this one good to? Would you say infinite?
For 10 tons?
Yeah, we're going to have exactly 10 tons of dust fall? No, it's not infinite. So how many sig figs do you suppose that is? Okay, it's either 1 or 2. When we have a 0 after the non-zero, it may or may not be significant. So what some people do is they'll put a decimal point. So if I wrote 10 with a decimal point here, then that's 2 sig figs. So if this is 2 sig figs, then it'd be anywhere from 9.5 to 10.4. However, if I don't put that little decimal, then typically we take this as 1 sig fig. So this is 2 sig figs, and this would be the precision window we'd expect. But if we have only 1 sig fig, do you know what this varies from? This will vary from anywhere from 6 to 14. You know, because we round it to the nearest 10 tons. And so we'd start with 0 tons, 10 tons, 20 tons, you know. And so what do you think would be more appropriate for dust fall? 2 sig figs or 1 sig fig? 2? Is it pretty consistent? What's that? Unpolluted air. Yeah, maybe it's 2 sig figs. Hard to say. Unpolluted air. But it depends on, you know, unpolluted. The source of dust could be soil, you know. So, for example, if there's a lot of vegetation versus no vegetation, so if you're out in the desert and there are winds, it's a windy day, not a windy day. I don't know if you've been in the desert, but sometimes you get these dust storms or dust clouds that blow in, make visibility very poor. So I think, you know, based on this, since they didn't put a decimal point here, I'm going to take this as 1 sig fig. So it's anywhere from 6 to 14 tons of dust. You know. But you'd think they could be more precise than that. But it's ambiguous. And so to get rid of that ambiguity, we use scientific notation, or we use decimal points to get rid of that. This one, how many sig figs? Infinite. This one, how many sig figs? 4. If you took Chem 4 here, they use 454. Even in Chem 1A, sometimes they'll use 454, but typically that 454 is only 3 sig figs. We want it to 4 sig figs. You can get it to more, or just look it up. In our book, it's listed to more than this. This one, infinite, and this one, infinite. All right, so we gotta get rid of square miles, so I need to square everything inside here. Okay, and this gives us square feet. So now we have tons per square feet, but we don't want square feet, we want square meters. So we need to get from feet to meters. How can we do that? We're gonna go feet to what? Yeah, we're gonna go from feet to inches and then inches to centimeters. So 1 foot is equivalent to how many inches? 12 inches. Okay, this one obviously you need to memorize, this one. I'm sure all of you already have it memorized, but then we'll have to square everything in here. So the grams cancel, actually milligrams don't cancel, we want milligrams there. And the miles squared cancels, and the feet squared cancels. And that gives me square inches. And then from inches we can go to centimeters. So in 1 inch, there's 2.54 centimeters. And then I'll square everything inside here. And so square inches cancel, that gives me square centimeters. And they want square meters. And so this one you should have memorized here. And then to go from centimeters to meters, it's going to be 100 centimeters per meter, and then square everything inside there. And so square centimeters cancel, and that leaves us per square meter. Okay, they don't want it per month, they want it per hour. And so we have to convert from months in the denominator to hours in the denominator. And so you could Google it, you know, how many hours are in a month. Do you know that? Do you have it memorized? No. But it's not going to be given, so we're going to have to do it based on conversion factors that we should know. And so we should go from months to what?
Days.
Days? How many days in a month?
365.
30 days?
Oh, never mind. I think it was a year.
30 days in a month, let's just say. Some months shorter, some months longer. We'll just say average. So the months cancel. And then, so this one memorized, this one we should have memorized. And this one, how many hours in a day?
24 hours.
24 hours. Okay, and the days cancel. And so this gives us milligrams of dust per square meter per hour. So let's go ahead and calculate it. It's going to be 10 times 2,000 times 453.6 times 1,000 divided by 5280 squared divided by 12 squared divided by 2.54 squared times 100 squared divided by 30 divided by 24. And so I calculate 4.8649 milligrams of dust per square meter per hour. Is that what you guys get? And then I'm going to assume we have one sig fig. You know, it could be one sig fig, two sig figs, or infinite. So we'll just assume it's one sig fig, and that's going to give me 5 milligrams of dust per meter squared per hour. And that's what the book gets. That's part A. Let's take a look at part B next. Part B, if the dust has an average density of 2 grams per cubic centimeter, so we have 2 grams of dust per cubic centimeter of dust. How long would it take to accumulate a layer of dust 1 millimeter thick? So we're going to coat some surface with 1 millimeter of dust. So how long will that take? So if we know the volume of dust, then we can get the grams of dust. And that's what we need for this. We need milligrams of dust. Because if we can get the milligrams of dust, we can relate it to the time here. And so in order to get the volume of dust, we need to know what the area is. If we get the area times the height, I know what the height is. So area times height is equal to the volume. And once I get the volume, then I can get the grams. Once I get the grams, I can get the milligrams of dust. And once I get the milligrams of dust, I can use the equation in part A. But I don't know what the area is. What is the area? Well, in one sense, the area doesn't matter. You know, the rate of accumulation will be the same. You know, we're getting 1 millimeter height. And so it's going to be a large area or a small area. To get that 1 millimeter height of dust, it's going to take the same. But to make this calculation easier to solve, I want an area because if I know the area, then I can easily calculate the volume of dust. And using the density, I can get the grams and then the milligrams of dust. And so this is what we do sometimes. You know, there are, let's say you're giving some kind of presentation, and a question comes up from the audience, and they ask you, you know, how long will it take How long will it take? They just want to know how long, but they didn't specify the parameters. You know, how long will it take? You know, if this and this and this are the conditions. And so what we do is, in that case is, you know, you need to know those parameters in order to solve the question. And so often what we do is we just assume one and to make our life easier for the calculation. And so if an area is not given, just pick one. What area will we pick? What area do you think might be the easiest? One
square meter.
square meter, yeah. And so what we're going to do is we're just going to assume an area, even though it doesn't matter, it's just easier for the calculation. Assume the area is equal to 1 square meter. Well, that's convenient because that's what this is. It's per square meter. And so sometimes this happens on exams. I've had tests where, you know, there are 2 unknown variables. If there are 2 unknown variables, how many equations do we need? Two equations. But they only gave 1 equation. And there was no second equation. So what do you do? Well, I'll tell you what some people did. Some people left the problem blank and then wrote. Not enough information to solve. You need. But other people solved it. You know how they solved it? They didn't derive another equation. They just assumed a number for one of the variables. They didn't assume any number. They just assumed reasonable numbers. So they said if variable A were this, so they pick a low side, then this is the answer we'd get. If variable A were this on the high side, this is what we'd get. And they'd expect the real answer to be between those 2 extremes. So we assume one at one extreme and another value at another extreme, and then border it. And so the answer is somewhere in between there. Does that make sense? And so in that case, it's much better, rather than to leave it blank, it's much better just to go ahead and try to make an assumption, what's a reasonable assumption, and then try to solve it from there. And so a meter squared, that's reasonable. Let's go with that. Okay, so if we know that the area is a meter squared and we know that the height is a millimeter, then we can figure out the volume of dust that's fallen. If we figure out the volume of dust, we can get the grams of dust. So let's go ahead and get the volume of dust from this. And so the volume of dust is going to be the area, 1 square meter, times the height, which is 1 millimeter. Well, these two aren't the same, so we're going to either convert millimeters into meters or meters into millimeters. Which way do you want to go?
I have a question. Can we find the volume of dust from the density that's given?
Yeah. We could find the volume of the dust from the density if they told us how many grams of dust fell on this.
So the grams would be from that to, okay. Because the average density is given, so I was thinking that we could find the volume of dust from that density.
Okay, that would be equivalent to this. What's the density of water? 1 gram per milliliter. Okay. If you have, let's say you have a bucket outside, how many milliliters of water will fill the bucket? In other words, how many millimeters of water will we get in that bucket? Can you tell based from the density? So that means only 1 gram of water will fall during a rainstorm. If you have a rainstorm, is it 1 gram of water that falls?
Per milliliter.
Or is it 1 milliliter of water that falls during a
No,
rainstorm?
1 gram of,
This-
1 gram of water falls per milliliter.
Yeah, 1 gram of water falls per milliliter. So either we need to know how many milliliters of water fell, or we need to know how many grams of water fell during the rain. So this is an intensive property. We need to know the extensive property, how much actually fell. So in this case, we don't know how many grams fell. And we don't know how many cubic centimeters of dust fell. This is just the density. This is not going to tell us how much actually fell. Does that make sense? And so we can't use this here.
The total amount.
Yeah, so what we have to do is we have to figure out how much, and in this case, we're not using the mass, we're going to figure out how much volume. So what we did was we assumed a square meter of area, and we assumed a 1 millimeter thick blanket of dust. And from that 1 millimeter thick blanket of dust, we can get the volume. And so the volume this is a composite unit, but we want it into a uniform unit. And so either we're going to convert meters into millimeters or millimeters into meters. Which one do you want to do? Should we get the volume in millimeters cubed, or should we get the volume in meters cubed?
Meters.
Meters cubed? Okay. We're going to get it in meters cubed. And so what I'm going to do is I'm going to convert millimeters into meters. So 1 meter is equivalent to 1,000 millimeters. And so this is going to come out to 0.001 meters cubed of dust. Well, it's still not quite there yet because I need the volume of dust in centimeters cubed. If I could get the volume of dust in centimeters cubed, then I can know how many grams of dust must have fallen here. And so what I'm going to do is I'm going to convert meters cubed into centimeters cubed. And so the conversion here is there's 100 centimeters in 1 meter. And then I'm going to cube everything in here. So I'm going to get 100 cubed, centimeters cubed, 1 cubed, meters cubed. And then I'm going to convert it from meters cubed of dust to centimeters cubed of dust. And so what does that come out to? This is 10 to the minus 3. This would be 10 to the 6. So 10 to the third. Is that right? 1.0 times 10 to the third cubic centimeters of dust. What did you guys get? Yeah, okay, 1,000 centimeters cubed of dust. Okay. And then I'm writing it to 2 sig figs, so that's why I wrote it in scientific notation. That's right, 1,000 centimeters cubed of dust. So we're going to have 1,000 centimeters cubed of dust fall on this square meter. Now we can figure out how many grams of dust that is. And so this is fixed. So we have 1.0 times 10 to the third cubic centimeters of dust. And then we know that there's 2 grams of dust for every cubic centimeter of dust. So 2,000 grams of dust fell on that square meter patch of land or whatever depositing on. So how long does it take to deposit 2,000 grams of dust? Well, what we need here is cubic centimeters of dust cancel. That leaves us with grams of dust. Do we have anything that gets rid of grams of dust or grams? We don't have anything that gets rid of grams of dust. And so what we'll do is we'll convert this to, we don't have anything that relates grams of dust, but we do have something that relates milligrams of dust. So what we're going to do is we're going to convert this to milligrams, 1,000 milligrams per gram. So now we have milligrams of dust. And what's going to relate that is we have this conversion. 5 milligrams of, oops, I need to flip it over. 5 milligrams of dust deposit on a square meter in 1 hour. And so here, the milligrams of dust cancel the milligrams of dust. And that leaves me with square meters and hours. We don't want hours. We want, well, what are they asking for? How long?
Yeah, how long?
Oh, then we could use, they don't tell us. So we're just going to leave it at hours. But I have a problem. I have this square meters. This is square meters, not of dust. This is square meters of area that's getting coated with dust. Does that make sense? And so how many square meters did I choose to use?
1.
Yeah. And so this is square meters of area. And I chose to use 1 square meter. So I'm going to just divide it by 1 square meter of area, so that the square meters of area cancel out the square meters of area, and that's going to leave me with hours. And so let's see how many hours this is going to take. So I'll have 1,000 times 2 times 1,000 divided by 5. .000 times 10 to the 5. We're only allowed, what is it, 2 sig figs? One sig fig. If we're allowed 1 sig fig, we could call this 400,000 hours. This seems awfully long, doesn't it? Because when I think about dust accumulation, it happens pretty fast inside the house. It doesn't take much time. Maybe the house has lots of polluted air. 400,000 hours. This is a dimensional analysis. This seems convoluted, doesn't it? Dividing by this to get rid of that. But that's what we do in dimensional analysis. We just work it, however it works out to cancel things out. Oops, did somebody write that?
Yeah.
Was that yours?
It's okay, I can put it
Carmen?
away.
Okay, you can put it back up. Do you remember this equation? Q is equal to mc delta T.
Yeah.
Do you remember that? Yeah. There are two things we could do. One is we could solve things using dimensional analysis like this. Or we can use an equation. Q is going to be in units of joules. M is in units of grams. C is the specific heat in joules per gram degree C. T is in degrees C. So this particular equation comes from dimensional analysis. That is, if I want to know how many joules, I got to get the grams to cancel. I can get them to cancel like this. And I got to get the degree C to cancel. And I get it like this. And therefore we derive an equation like this. It's the same thing as this. This equation comes from dimensional analysis. Dimensional analysis, I'll just abbreviate DA. So this is similar in that sense. So if I have, let's say I have 5 milligrams per meter squared per hour. This is dust. And I'm going to call this, what should I call this? Not C. I'll call this dust fall, so I'll call it D. Okay, if I want how much dust falls, what do I need to multiply this by? So if I'm looking at dust, milligrams of dust, so I need to cancel out what? I need to cancel out meter squared. In order to cancel out meter squared, I need the area. So the area in meters squared, so the meter squared cancel. And what else do I need to cancel out? I need to cancel out hours, so I need the time in hours. So I come up with this equation. I come up with the milligrams of dust fall is equal to area times d times t. T for time. And if I solve for time, what does the equation come out to? If I solve for time, then I need to know the milligrams of dust over the area over d. And so basically what I did here, do you see I inverted d? That's like dividing by d. And I had to divide by the area. So I had to divide by the area. And so basically I solved this using dimensional analysis, but if I were given the equation, I could have used the equation to solve it. The time is equal to the milligrams of dust here, divided by the area, divided by d, which is invert and multiply. And so this brings up an experience I had in at UCLA. At UCLA, I wanted to take an engineering class. I took like 2 engineering classes. I wasn't an engineering major, but you could still take the class. But there was something called Intro to Engineering, which is a lower division course. I wanted to take an upper division engineering course. And the prereq was Intro to Engineering. So I petitioned the engineering department to let me skip Intro to Engineering because I was already an upper level chemistry student. So I figured Intro to Engineering, if there's something I need to know, I can just learn it by myself. And so they accepted my petition, and so I skipped Intro to Engineering and went straight into the engineering class, which is the upper division. While I was in the engineering class, we had a test. And on the test, the instructor just gave a whole bunch of numbers like I listed up here, but no equation. And, you know, and then he asked us to solve for something, like the time. And I was pretty surprised because I thought it was a pretty easy problem. I thought it was a pretty easy problem because of dimensional analysis. I'll just figure it out using dimensional analysis. But what surprised me was, after the test, I was talking to some of the other students, and a lot of them didn't get the answer. They couldn't figure it out. And the reason they gave that they couldn't figure it out was because the equation was not in the book, and the instructor never gave the equation for it. And so then I thought, wow, you know, it's like this. If somebody gave you a whole bunch, like somebody gave you the mass, somebody gave you C, and somebody gave you delta T, but they didn't give you the equation, could you figure it out? You know, and so these students were saying they couldn't figure it out because the equation wasn't given, but all the variables were given with the units. And so in other words, Intro to Engineering must not have covered dimensional analysis very much, and maybe in the chemistry they didn't cover dimensional analysis very much because it was just a simple dimensional analysis problem. And so we could use dimensional. In fact, a lot of these equations, like this equation, the Q is equal to MCAT, a lot of people memorize this. Q is equal to MCAT. You don't even have to memorize this because you're given the numbers. You can just figure out what you need to multiply and divide in order to get the desired unit. You know, but I remember memorizing this, Q is equal to MCAT, but in reality you don't need to memorize that equation. Even the ideal gas law, I mean, you don't need to memorize that if you know what R is, you know. If you know what R is, 0.08206 liters times atmosphere per mole Kelvin, well, that was given on the test. You know, this is like the problem here. This is why it surprised me so much. And so they gave you the, let's say they gave you the volume. And the volume is this many liters. And let's say they gave you the pressure. The pressure was this many atmospheres. And let's say they gave you the temperature. The temperature was this many Kelvin. And they asked you to solve for moles. They couldn't solve for moles because they weren't given the equation. You know, obviously the equation is easy. N is equal to PV over RT, right? But maybe they forgot it. You know, a lot of people memorize the equation. It's perv nerd. Have you heard of perv nerd? Perv nerd. A lot of people memorize it that way. But you don't need that. You don't need that because all you have to do is cancel out the units to get the desired quantity that you want. And so that was an interesting experience. So 2 interesting experiences I had at UCLA. One was this. The other was they didn't give you all the variables. And so what did you do? So some people left it blank, some people assumed a number. You want to assume a reasonable number. You don't want something, you know, way out there. And so you assume a number or a range, you know, the low and the high, and then calculate it. And so some people left it blank. If you leave it blank, you get 0 points. No partial credit, you know. And so you assume it, and then you can solve. Okay, let's look at the next problem, 75. In the United States, the volume of irrigation water is usually expressed in acre-feet. 1 acre-foot is a volume of water sufficient to cover 1 acre of land to a depth of 1 foot. 640 acres is equivalent to 1 square mile. 1 mile is equal to 5,280 feet. So this is just area times depth. The area is 1 acre, and the depth is 1 foot. So if we cover 1 acre with 1 foot of water, then we have an acre foot. And so it's just a weird unit. It's a weird unit because 1 acre foot because they aren't the same unit. That's it. And so this is like the earlier problem where we had 1 square meter covered in a depth of 1 millimeter. And so the volume is, if we left it as is, the volume would be 1 meter squared millimeter. And so the area is meter squared, the depth is millimeter. And so this would be a composite unit here. This is another composite unit here. The area is acres, the depth is feet. So we don't like to leave it like that, you know. There's no such thing as cubic acres. So we'll try to convert it to something else. Okay, let's go on here. The principal lake in California, in the California Water Project, is Lake Oroville, whose water storage capacity is listed as 3.54 times 10 to the 6 acre feet. So Lake Oroville has a volume of 3.56 times 10 to the 6 acre feet. 3.54, sorry. 3.54 times 10 to the 6. In other words, 3,540,000 acre feet. express the volume. Well, Lake Oroville is not filled to capacity, even after the big storms. I think it's still like 80 feet short of being full. But we'll assume it's full. Express the volume of Lake Oroville in cubic feet. So we have the height in feet. If we can get the area in square feet, then we're good for this one. So we'll do part A here. Part A is we want to leave the feet in there, but we want to get rid of the acre. And so how can we get rid of acres? Yeah. And so 1 mile squared is equivalent to 640 acres. How many sig figs is this? You say? Is it 2, 3, or infinite? Actually, this is exact. This is by definition. And so there's exactly 640 acres in a square mile. I don't know how they picked that, but that's it. How about Lake Oroville, the volume here? 3 sig figs or infinite? 3. So far we have 3 sig figs. Acre cancel, that gives us another composite unit, miles square feet. But we don't want miles square feet, we want to convert miles into what? Feet. Yeah. And this one you don't need to memorize because we don't use it that often. 5,280 feet in 1 mile. But it's squared, so we have to square everything in here. And so square miles cancels this. And now we have square feet times foot. A square feet times foot is going to give us cubic foot. And that's what we want. So let's see what this comes out to here. What did you get?
1.54 times 10 11.
Okay, 1.54. Give me one more digit.
2.
1.542 times 10 to the 11
Yeah.
cubic feet. We're allowed 3 sig figs, so I want you to show me 4 and then round it to 3. And so if we round it to 3, it goes to 1.54 times 10 to the 11 cubic feet. And if I want this in times 10 to the 9th, this would be 154 times 10 to the 9th cubic feet. 10 to the 9th is what? Billion, trillion? What is it? 154 billion cubic feet. So Lake Oroville contains 154 billion cubic feet of water, if I did this correctly.
So how does in the quiz, we can, in a quiz or a test or anything, we can just do any of those answers right there? Or you want a selected answer?
No, any of these is fine. Doesn't matter. Okay. All right, they want it in cubic meters. Does that seem pretty straightforward? Yeah. They want it in gallons here. But what I don't want to see is I don't want to see some weird conversion factors that you look up. You know, we want to try to do these things based on the conversion factors that we all use regularly. So let me just take a look at gallons for this. So we're going to start off in acre feet, and then we're going to convert it to acre. We're going to convert it to miles squared feet. Okay, this is using the conversion factor given here. And then we're going to go from miles squared to feet, cubic feet, and then from cubic feet we go to cubic inches, because we know that there are going to be 12 cubed inches cubed per 1 cubed foot cubed. So this is a normal conversion factor, not anything weird that we'd have to Google. And then from cubic inches we're going to go to cubic centimeters. Cubic centimeters, this one everybody should know. There's 2.54 centimeters cubed per 1 cubed inch cubed. Right? And so this is just a standard conversion. And then from centimeters cubed, we're going to go to milliliters. This one everybody should know. 1 milliliter is the same thing as 1 cubic centimeter. And then we're going to go from milliliters to liters. And then from liters to gallons. This one, if you forget, it's all right. 1 gallon is equivalent to 3.785 liters. This is 4 sig figs. But these are your normal conversion factors. Okay, let's look at 76. Fahrenheit and Celsius thermometer are immersed in the same medium. At what Celsius temperature will the numerical reading on the Fahrenheit temperature be? 49 degrees less than that on the Celsius thermometer. So let's take a look at the temperature scales. Yeah, and then we'll answer this question. So if we have a Celsius thermometer, the two temperatures of 0 degrees C and 100 degrees C. Zero degrees C is the freezing point of water, and 100 degrees C should be the boiling point of water. So what we do is we use this to calibrate the thermometer. So if you put this in ice water, it should be reading 0 degrees C. If you put it in boiling water, it should be reading 100 degrees C. So you can see if your thermometer is off a little bit. So we can calibrate it. If we put a Fahrenheit thermometer into ice water, what should its temperature reading be? 32. So 0 degrees C is equivalent to 32 degrees Fahrenheit. And if we put the Fahrenheit thermometer into boiling water, its temperature should be exactly 212. So we can do the same thing, it's just off. And so we came up with what's something called the ambient temperature. The ambient temperature is the degrees Fahrenheit is equal to 9/5 the degrees Celsius plus 32 degrees. And so we derived that equation the other day. But we can also have something called the change in temperature, delta T. And so this is a bit different. If the temperature were 100 degrees C, what would the Fahrenheit temperature be? 212. But what if the temperature increased by 100 degrees C? If the temperature increased by 100 degrees C, did the Fahrenheit temperature increase by 212 degrees Fahrenheit? No. And so if the temperature is 100 degrees C, then the temperature is 212 degrees Fahrenheit. But if the temperature increased by 100 degrees C, then the Fahrenheit did not increase by 212 degrees. What did the Fahrenheit increase by? 180. And so when we do a change in temperature, it's different than when we look at the ambient temperature. And so the ambient temperature is like the elevation. When you measure the elevation, let's say of a mountain, we typically measure it in reference to sea level. So how many feet above sea level is that mountain? Mount Whitney's 14,500 feet above sea level. But the elevation is going to depend because we can also measure relative to the center of the Earth. And we're going to get a different elevation relative to the center of the Earth. But when we look at delta T, that is, what is the elevation from the base, or that is, how tall is the mountain? How tall the mountain is, Mount Whitney is only about 2,000 feet tall. (2,000 feet tall from the base to the top, I think. Or maybe a little taller. Maybe 4,000 feet tall. Depending on what you call the base. And so this is our delta elevation, but our absolute elevation is going to depend on where we reference it to, sea level or the center of the Earth. Our ambient temperature is like the absolute temperature. It's going to depend on what the zero is. And the zeros are offset. So the Fahrenheit 0 is offset from the Celsius 0 by 32. There's 32 more degrees Fahrenheit to get to 0 Fahrenheit. But when we look at delta T, then it's like this. There are 180 degrees Fahrenheit for every 100 degrees Celsius. So this is the relationship we use when we look at a temperature change. This is the relationship we use when we look at what the ambient temperature is. So let's say I had a 10 degree C temperature increase. If I have a 10 degree C temperature increase, then what is the Fahrenheit temperature increase? 18 degrees. If I had a 1 degree C temperature increase, so a 1 degree C temperature increase means how much did the Fahrenheit change? 1.8. But let me ask you this. If the temperature, the ambient temperature were 1 degree C, then what is the Fahrenheit temperature? So if the temperature were 1 degree C, that's 1 degree above 0 here. And so we increase the Celsius temperature by 1 degree C above the 0. What would the Fahrenheit temperature be? 33.8. And so 1 degree C ambient temperature is 33.8 degrees Fahrenheit ambient temperature. Does that make sense? And so we have to be careful. We have to be careful. Are we talking about a temperature change, or are we talking about the ambient temperature? Because we use two different equations to handle that. One, we use dimensional analysis to handle temperature change, and then two, we have to use this. This part, the first part of this is just dimensional analysis because 9 is 180, 5 is 100. So this is 180 over 100. Same, so this is 9/5. 9 degrees Fahrenheit for every 5 degrees Celsius change. This is like I have this European car, and I guess the knob is calibrated for Celsius. So I turn the knob up just like, when I turn the knob up, I turn it up like 1 degree Celsius. Well, I turn the knob up, I want to warm up the car by 1 degree Celsius, which is equivalent to what in Fahrenheit? 1.8. Whereas my previous car, I could turn up the temperature by 1 degree Fahrenheit. So if I was a little cold, like this room's pretty cold, I'd turn up the temperature by 1 degree Fahrenheit, right? But in my car, I could only turn it up by 1 degree Celsius. And so this is the weird thing. It got too warm. So I turn it up 1 click, it's too warm. Turn it down 1 click, it's too cold. I want something halfway between. And I wish my knob were set with Fahrenheit because it has finer adjustments to it. And so it's a pretty big jump here. All right, so again, this would be delta T. All right, so what we're doing is we're looking at not temperature changes, we're looking at the ambient temperature. So right now, if I'm at 0 degrees C, the Fahrenheit temperature is plus 32, 32 greater. If I'm at 100 degrees C, it's 212, so it's plus 112 degrees greater. So is there a temperature here where it's 49 degrees? Less than that, the Celsius. And so that means, is there a temperature here where the Fahrenheit would be 49 degrees less? What do you think? Maybe. What we can do is we can just make gigantic thermometers and then look, at this Celsius, what's the Fahrenheit? But that would take too much time. And so is there a way to do this mathematically? And the answer is yes. There's a way to do this because this is two unknowns. Two unknowns. So for example, this would be 76A. I don't know what the Celsius temperature is, and I don't know what the Fahrenheit temperature is. And so my x, which is Celsius, is unknown. My y, which is Fahrenheit, is unknown. So if x and y are both unknown, what do I need? I need the system of equations. I need two equations. So can you think of one equation? Well, one equation is going to be degrees Fahrenheit is equal to 9/5 degrees Celsius plus 32 degrees. Okay, what's my second equation?
Degrees Celsius equals degrees Fahrenheit minus 32 times 5 nines.
Okay, that would be the same equation though, mathematically. So if we solve this for degrees Celsius, then equation 1 and equation 2 are kind of the same. We need a unique equation for equation 2. So let's go back to the problem. The problem says, at what Celsius temperature will the numerical reading on the Fahrenheit temperature be 49 degrees less? And so at what Celsius temperature will the numerical reading on the Fahrenheit temperature be 49 degrees less? And so the Celsius should be reading 49 degrees lower than the Fahrenheit temperature. And so that would be equation 2. And so now I have two unknowns and two equations. What do I do? I just at what Celsius will the Fahrenheit, wait, did I get this right? At what Celsius temperature will the numerical reading on the Fahrenheit be 49 degrees less than the Celsius? Oops. At what, okay, will the Fahrenheit reading be 49 degrees less than the Celsius? Sorry, I got that wrong. And so the Celsius should be, is that right? Yeah? Okay. And so what do I do now? I have two equations, two unknowns. What do you do next?
You plug in the second.
Yeah, let's substitute. So we'll plug in the second. And so degrees Fahrenheit, I'm going to substitute this in for this. So I'm going to get degrees Celsius minus 49 degrees is going to equal 9/5 degrees Celsius plus 32 degrees. So now I have it in one variable, x. Okay, so what I'm going to do is I'm going to subtract this degree C from both sides. And then subtract 32 from both sides. So if I subtract, this is going to be minus 81 degrees is equal to, I'm going to call this 5/5. So 9/5 minus 5/5 is going to give me 4/5 degrees C. And therefore degree C is going to equal 5/4 times minus 81 degrees. And so 5/4 times minus 81. So 5 times 81 divided by 4. 101.25. So my degrees Celsius is 101.25 degrees Celsius. If my degrees Celsius is 101.25, I'll plug that in here and minus 49. Actually, it's negative. Negative 1 or 1, sorry. And so that means my degrees Fahrenheit must be minus 101 minus 49 is going to be minus 150.25 degrees. Fahrenheit. And so my Celsius reading is 49 degrees less than my Fahrenheit reading. Let's double check this. I'm going to double check this by calculating it. So I'm going to calculate my degrees Fahrenheit based on my Celsius that I just got. And so my degrees Fahrenheit is equal to 9/5. My degrees Celsius is 101.25 negative plus 32 degrees. And so let's calculate it. Times 9 divided by 5 is 32. And this comes out to negative 150.25 degrees. So it checks. It's okay. So that worked out. Both of those are sensible temperatures, so it's feasible. If you got a temperature that's not feasible, like what's a temperature that's impossible? Yeah, below 0 Kelvin. So if you had minus 300 degrees Celsius, no, it's impossible, because that's below 0 Kelvin. If you had something below minus 454 Fahrenheit, then that's impossible too, because that's below 0 Kelvin. All right, B, twice that on the Celsius thermometer. So equation 1 is going to be the same, but equation 2 will be different. What would equation 2 for B be?
Degrees Fahrenheit equals degrees Celsius times 2.
Yeah, okay, degrees Fahrenheit is equal to 2 times degrees Celsius, and then just substitute. C, 1/8 that on the Celsius thermometer.
Instead of 2, it's 1.
Yeah, instead of 2, 1/8. D, 300 degrees more than that on the Celsius.
Degrees Celsius plus 300.
Yeah, degrees Celsius plus 300. And so we have 2 equations, 2 unknowns for those. Okay, so you could do those. Uh, 77, the accompanying illustration shows a 100 milliliter graduated cylinder. .0. Half filled with 8.0 grams of diatomaceous earth. So we're going to fill this halfway with diatomaceous earth. So this is going to be 50.0 milliliters of diatomaceous earth. Diatomaceous earth I'm going to just call DE. A material consisting mostly of silica and used as a filtering medium in swimming pools. Do you know where diatomaceous earth comes from? You know, I'm familiar with diatomaceous earth because I was a geology major in Santa Barbara, and there's a huge diatomaceous earth mine near Santa Barbara. And what it is just fossilized marine organisms. And this is like the shell, the skeleton of those marine organisms. This is what it looks like. Magnified. This is what it looks like to your naked eye. And then if you magnify it, this is what it is. So these are just, you know, this looks like it's like manufactured, but these are all from marine organisms. And this is kind of the shell or the skeleton of the marine organisms. So this is the remains. And they use this as a filtering medium. See, it's probably pretty good. Yeah. But it's just broken up shells or skeletons. This is made out of silica. Silica is like glass. And so if you spray hydrochloric acid on this, it doesn't dissolve. A lot of other shells are made up of carbonates, which would dissolve in acid. This does not dissolve in acid. How many milliliters of water are required to fill the cylinder to the 100 milliliter mark? We've got 50 milliliters of diatomaceous earth. Don't I just need 50 more milliliters of water to fill this? So this consists of 50 milliliters of diatomaceous earth and 50 milliliters of water, and that gives me 100 milliliters? Would that work? No, why not?
Because there's going to be like some sort of space in between the earth and how it absorbs water.
Yeah, right. Yeah. This is like grains of sand, although the sand would be hollow. And so the water is going to seep in here. And how much water seeps in there? Because there are things called grain boundaries and void spaces and other stuff. And so if this were solid diatomaceous earth, yes, then we'd need 50 milliliters of water, but it's not. It's just a whole bunch of broken up little particles of diatomaceous earth and air. So this 50 milliliters isn't just diatomaceous earth. It's diatomaceous earth plus the air that's in between. This is why I drew it dotted like this. It's not a solid chunk of diatomaceous earth. What else do they tell us? Well, they tell us that it has 8.0 grams of diatomaceous earth. The diatomaceous earth is insoluble in water and has a density of 2.2 grams per cubic centimeter. So we have 2.2 grams of diatomaceous earth per cubic centimeter. Well, we have the volume here and the mass. If we look at the volume and the mass here, we have 8.0 grams divided by 50.0 milliliters. 8.0 grams divided by 50 milliliters gives us a density of what? So it's 8 divided by 50, 0.16. Grams per milliliter. So the density of this diatomaceous earth and air is only 0.16 grams per milliliter, compared to the density of the diatomaceous earth itself, which is 2.2 grams. So how can we figure out how much water is going to be added here? So the way we have to do this is we have to figure out what the volume of the diatomaceous earth itself is. And so if we know how many grams of diatomaceous earth we have, 8.0 grams of diatomaceous earth, and we know what the density is, 1 cubic centimeter per 2.2 grams of diatomaceous earth, then we can get the volume of diatomaceous earth in cubic centimeters or milliliters. So let's just get in milliliter. And that is 1 milliliter is the same thing as 1 cubic centimeter. And so the actual space that the diatomaceous earth takes up is going to be 8 divided by 2.2. It's 3.63 milliliters. So what that means is that this 50 milliliters is equal to 3.63 milliliters of diatomaceous earth plus how many milliliters of air? 46.37 milliliters of air. Plus we have 50 milliliters of empty space above here. And so we're going to have to fill all that air with water. And so we're going to have to add 96.37 milliliters of water. Since the diatomaceous earth actually took up very little volume, it was mostly air, because those things are hollow and they're gaps. Does that make sense? So that's a lot of water, even though this took up, or appeared to take up, so much volume. Didn't really. And so here they show the diatomaceous earth. I don't know what happened to it. Looks like there's 20 milliliters of diatomaceous earth missing. And so this isn't so accurate. It's more dense than water, so it should stay at the bottom. Okay, the simple device pictured here, a picnometer, is used for precise density determination. From the data presented, together with the fact that the density of water at 20 degrees C is 0.99821 grams per milliliter, determine the density of methanol in grams per milliliter. All right, the first thing is the density of water changes with temperature. If I round the density here to 1 sig fig, what is it? 1 gram per milliliter. If I round it to 2 sig figs, what is it? Not 0 point.
It's
1.0. So to 2 sig figs, it's 1.0 grams per milliliter at 20 degrees C. If I round this to 3 sig figs, what is it? It's not 1.00. Because 3 sig figs means dropping the 2. If I drop the 2, do I round up or do I leave it? I leave it. So if I drop the 2, I leave it. So to 3 sig figs, it's 0.998. To 4 sig figs, it's 0.9982. To 5 sig figs, it's 0.9821. So when we say that the density of water is 1, you know, for sure that's valid to 1 sig fig. Is it valid to 2? Yeah, probably 1.0. But to 3 sig figs, can we say the density of water is 1.00? Well, it depends on the temperature. And so going to 3 sig figs might be pushing it. And so most people memorize the density of water to 2 sig figs. Easy enough, 1.0. Determine the density of methanol in grams per milliliter. So let's see the data here. We have an empty picnometer. The empty picnometer is this glass, and this glass thing weighs 25.601 grams. And then you fill it with water. At 20 degrees C, it's 35.552 grams total. What we can do here is we can figure out how many grams of water we added. If we know how many grams of water we added to fill this, then we can figure out the volume of our picnometer. The volume of the picnometer, we just use the grams of water and the density, and we can get the volume. And so let's go ahead and figure out what the volume of the picnometer is. Here. Okay, so the first thing is we need to know how many grams of water we just added there. And so the grams of H2O is going to equal the picnometer plus water, which is 35.552 grams, minus the picnometer, which is 25.601 grams. How many sig figs am I allowed in my answer? Maybe 5. Actually, I don't know because this is subtraction. Addition and subtraction, we don't do it by sig figs. We do it. I shouldn't have asked how many sig figs. I should have asked you how many decimal places. How many decimal places am I allowed in the final answer? 3. Okay, so let's go ahead and do this one. This is going to come out 1, 5, 9, 9. So I get 3 decimal places. 3 decimal places minus 3 decimal places gives me 3 decimal places. But this is 5 sig figs minus 5 sig figs. We end up with 4 sig figs. And so addition and subtraction, we don't care about sig figs. We care about decimal places. And so this is how many grams of water. So this is the grams of picnometer plus water. This is the grams of picnometer. And so subtract the 2, I just get the grams of water. If I know how many grams of water I have in this picnometer, I can figure out the volume by using this density. This density is quite precise. And so the next thing I'm going to calculate is the volume of the picnometer, which is going to be 9.951 grams of water times the density, which is going to be 1 milliliter per 0.99821 grams of water. So what is the volume of the picnometer here? 9.951 divided by 0.99821. I get 9.9688. 9.9688 milliliters. Since the milliliters of water and the milliliters of the picnometer are the same, this is going to be the volume of the picnometer. And how many sig figs am I allowed? Well, this is multiplication and division, therefore I have 4 sig figs and 5 sig figs. I'm going to be allowed 4 sig figs in my final answer. So this is going to be 9.969. This isn't my final answer. Since this isn't my final answer, I might carry an extra digit here. If this were my final answer, I'd round it, 9.6969 milliliters. And so if I'm going to do another calculation, I might use this one instead, carry an extra digit to minimize rounding error. Okay, now we fill the picnometer with methanol. And so what we can do is we can figure out how many grams of methanol we have. Here next. And so the grams of methanol, methanol is abbreviated MEOH. And is methanol okay to drink? No, don't drink methanol. Why? It's poisonous. Okay? And it can cause blindness, permanent blindness, and death. Every year, people die or go blind from drinking methanol, unfortunately. There was this recently in the news. There was some. I saw there's some Americans traveling, I think, in the Bahamas, someplace. One of them went to the bar and got drinks and was dead next day. And so they're wondering what happened. You know, why did this apparently healthy person die? So I had a theory. Should I say theory or should I say hypothesis? I should say hypothesis because the theory should be what? Well accepted, right? It should have widespread acceptance. My hypothesis is that maybe the alcohol was spiked with methanol, you know, and so I'd have the drinks tested there because methanol is a lot cheaper to make than ethanol. Ethanol is okay to drink, you know. But I was thinking maybe the alcohol was spiked with methanol since it's cheap to make because all you need to do to make methanol is to ferment wood. And wood is a lot cheaper than fermenting sugar or grain. You'd have to ferment sugar or grain to make ethanol. And so we could test the hypothesis by just analyzing the drinks there, you know, see what the methanol content was. In fact, you know, the hand sanitizers, the FDA does not recommend using methanol hand sanitizers because methanol is somewhat poisonous.
poisonous, like, how much of it do you have to ingest before you're blind or?
Well, people ingest small quantities of it sometimes, and you end up with a headache, but nothing permanent damage. And so I think it's a pretty large quantity that you would have to ingest, but I don't know exactly because they have something called the LD50. Have you heard of that? A lot of chemicals are rated by the LD50. And the LD50 means lethal dose for 50% of the population. So if you give that quantity to a population and 50% of that population dies, that's the LD50. So 50% might survive, 50% might die. And so you'd want to know the LD50 for methanol. And you can find the LD50 for methanol. It's going to be online somewhere, but I don't recall the number. So you might survive, you might not. Some people can, the LD50 for arsenic is pretty high, but some people have built a tolerance for arsenic that's like a crazy tolerance for arsenic, so they can consume lots and lots of arsenic and still not die, That's because they've been exposed to little bits. There's arsenic in rice, and there's arsenic in water, and there's arsenic, and so if you've been exposed continuously, I guess you built some kind of tolerance to it, compared to people who don't. So it's tricky. How much does it take to kill you is always tricky to determine. Yes. And so the LD50 would be good. But anyway, methanol is a bit dangerous. And it's not the alcohol that's found in alcoholic beverages. But we can figure out the grams of methanol by taking the grams of picnometer on methanol, which is 33.490. 33.490 grams. And so when it's addition and subtraction, I like to line up the decimal places so I can see. Minus 25.601 for the picnometer. So this is the pic and methanol. Methanol, I abbreviate MEOH. And this is just the pic. And so what are we going to get for grams of methanol? $33.49 minus 25.601. 7.889 grams of methanol. And so the density of methanol is equal to the mass of methanol divided by the volume of methanol. So the mass is 7.889, and the volume is the volume of the picnometer, which is 9.969 milliliters. So divided by 9.969, and that gives me a density of 0.791. How many sig figs are we allowed? 3.5 grams per milliliter. Okay, now this is the final answer. So I'm going to round this. I have 4 sig figs, so I'm allowed 4 sig figs. So 0.7914 grams per milliliter. So this is a little less dense than water, a little lighter than water, 0.8 roughly. If the picnometer of exercise 78 is filled with ethanol, is ethanol okay to drink? Yeah. Well, you can still die from ethanol, but the LD50 is huge. You'd have to consume a huge amount. The observed mass is 33.470, so we have the mass of ethanol plus picnometer. So we could do the same calculation. What is the density of the ethanol? So exact same calculation. So I'm not going to do it unless I have to do it. How precisely could you determine the composition of an ethanol-methanol solution by measuring its density with a picnometer? Assuming that the density of the solution is a linear function of the volume present. So this is a totally different problem here. This is a problem of a mixture. And in a mixture, we need to know how much methanol and how much ethanol. If we need to know how much methanol and how much ethanol, that's two unknowns. If we have two unknowns, what do we need? Two equations. But there's another way to do two unknown, two equation type problems. And so I'm going to show you that. When we have two unknowns, like a mixture like this, mixtures can be solved like system of equations, or mixtures can be solved by using the graphical method. And so I'm going to show you the graphical method for this particular problem, but we'll take a break first.